We're going to get started here on our next unit in the course, and I wanted to take a minute to kind of introduce you to these Unit 2 functional groups. All right, so our first functional group that we're going to cover has these hydroxyl bonds. What's our functional group here? These are alcohols. All right, what distinguishes alcohols are those hydroxyl groups. If we take that oxygen in our alcohol and we replace it with that other member of that same family on our periodic table, sulfur, sulfur's got those same bonding patterns of 2 bonds and 2 lone pairs. So this is like our sulfur analog to an alcohol. We call these thiols. Like alcohols have that OH group, thiols have that SH group. All right, if we take our alcohol and we move that oxygen to the middle of the molecule, so now we have an oxygen between 2 carbon atoms, we consider this to be a different functional group. This is an ether. So an ether necessarily has that oxygen bonded to 2 carbons. There's a very special ether that we're going to spend a lot of time discussing. It turns out that ethers are kind of a boring functional group. They don't really have very many reactions. But there's one very special ether that we're going to spend a lot of time talking about because it is very reactive. And that is if we take those same 3 atoms, but we cram them into this 3-membered ring here. This is what we call an epoxide. All right, epoxides, 3-membered rings are very unstable, and so these epoxides are much more reactive than other ethers. All right, and now we're going to take our ether with our oxygen between these 2 carbons, and we're going to sub it out for that same family member, sulfur. So now I have a sulfur that's between 2 carbons. This is what we call a sulfide. Cool, so these are going to be kind of our focus of the second unit in the course, these functional groups here. Pretty much we're going to follow the same format when we introduce a new functional group. First thing we do is we learn how to name it, so we'll talk about nomenclature, and then we dive into the reactions and properties of those functional groups, and then some of those reactions we learn mechanisms for as well, right? So that's going to kind of be the design of the course going forward. We're going to see the same format. Our first functional group that we're going to focus on are the alcohols. Before we do that, though, now that we're looking at these kind of on bulk here, I wanted to take a second and discuss the physical properties of these functional groups here. All right, and specifically we want to start thinking about the polarity of these different functional groups. All right, and as long as we take molecules that have a similar size to them, so I specifically chose a 2-carbon version of each one of these here, we can get a sense of the intermolecular interactions that they have with one another. By that I mean how strongly are neighboring ethanol molecules interacting with one another. If I have a beaker of ethanol, how strong are those interactions between neighboring molecules? We can get a sense of that strength by looking at the boiling point of that compound. right? In order to boil something, we need to take it from the liquid phase where they're interacting with one another, and we need to break those interactions in order to put them in the gas phase. So those boiling points are a good measure of how strongly molecules are interacting with one another, all right? So when we're thinking about polarity, we're going to be thinking about our boiling points, or rather we're going to be using our boiling points. We can measure the strength of those intermolecular interactions. Using boiling point. All right, so looking at these, we're going to focus on these four functional groups here. Which one do we think is the most polar molecule up here? Our alcohol, our thiol, our ether, or our sulfide? Anybody got a guess here? I heard it. So it's our alcohol. Why our alcohol? What does this have that's so special? It's got that OH, so we call those interactions between neighboring molecules hydrogen bonding interactions, right? That OH group is one of those special groups that are capable of those strongest type of intermolecular forces, hydrogen bonding. And so indeed, if we were to take this alcohol here and look at its boiling point, we would find that it has the highest boiling point of all of these compounds. All right, so looking at boiling point, this has a boiling point around 78 degrees Celsius. All right, and that's because it forms those strong hydrogen bonding interactions. Right, because it's got those strong interactions, that's what makes this the most polar of our molecules. So I'm going to say highest boiling point here at 78 degrees. That's our alcohol, indicating that it is also the most polar of our functional groups. Next, we have our thiol here. Thiols, if we measure our boiling point of this 2-carbon thiol specifically, we would find it has a boiling point of 35 degrees Celsius. So these do not interact with neighboring thiols quite as strongly. And that's because it cannot hydrogen bond. An SH group is not capable of hydrogen bonding. We would call that simply dipole-dipole interactions. All right, remember, hydrogen bonding is just kind of a special category of dipole-dipole interactions that are just that much stronger. But you have to have one of these really tiny, really electronegative elements in order to do hydrogen bonding. So sulfur is just less electronegative than oxygen. So the strength of those intermolecular interactions is decreased. All right, our lowest boiling point compound. So the next two here might be a little bit of a surprise, but our lowest boiling point compound is our ether. All right, a dimethyl ether, these 2-carbon ethers here, have a boiling point of negative 24 degrees Celsius, meaning that it's not even a liquid at room temperature. These would be gases at room temperature. Their boiling point is less than that of room temperature. This is still technically a polar molecule here. It has this tiny little dipole in it, but it has very weak dipole-dipole interactions. All right, and I guess I'm going to kind of squeeze in here just for context. If we take a similar sized alkane, our most nonpolar functional group, so propane here, has a boiling point around negative 48 degrees Celsius. So that oxygen does increase the strength of those intermolecular interactions a little bit, just nothing crazy. Still pretty freaking low boiling point. All right, these alkanes, completely nonpolar. They have what are called only dispersion forces available. All right, our last one are sulfides. This is kind of an interesting topic here. Points out a subtle aspect of polarity that hasn't really been discussed up until this point. Our sulfide here has a boiling point that is also around 35 degrees Celsius. Very similar to our thiols. All right, so why is that? There's one term that we've thrown around a lot with regard to polarity, and that is electronegativity. Right? Something's ability to pull electron density in a bond gives you an idea of how polar or nonpolar a group of atoms are. There's another aspect of polarity, though, that turns out to be really important, and that has to do with the size of an atom. All right, so sulfur being a much larger atom, its electrons are much further away from its nucleus. So it's not holding on to those electrons as tightly as, say, an oxygen atom is. An oxygen atom we can think of as like a hard shell of electrons, whereas a sulfur atom, these larger atoms, are much more squishy shells of electrons. All right, this is a property we call polarizability. So sulfur, this also forms these, or sulfide rather, also forms these dipole-dipole interactions. But why are they so much stronger than my ether? My ether has a boiling point of negative 24 compared to my 35 for my sulfide. So clearly these are interacting with neighboring molecules much more strongly. So why are these dipole-dipoles interactions so much stronger? Because sulfur is more polarizable than oxygen. All right, and that term polarizable means that its electrons are held further / less tightly to the nucleus. Remember, polarity is all about having this disparity of electron density. One region of your molecule has a lot of electron density, the other region of your molecule doesn't. Well, if your electron cloud is really squishy and can move back and forth very easily, this makes it easier to create regions of high electron density and low electron density. All right, so again, thinking about the polarity of these molecules, we can think about boiling point as a measure of the strength of our intermolecular interactions. I want to put a very important caveat here. This only works for molecules of a similar size. Okay, so just kind of comparing these different functional groups that we're going to encounter in this unit. And again, we're going to kind of then take each one by one and kind of do a deep dive on those. So we're going to start out with our first functional group here. This is the focus of chapter 17 in our textbook. Alcohols. All right, so our functional group here, again, would be considered an alcohol. Alcohols necessarily have these OH bonds here. We have a special name for that bond. This is what we call a hydroxyl group. All right, so alcohols necessarily contain hydroxyl groups. Similar to how like a ketone contains a carbonyl group, right? We have a special name for certain bonds. Our OH bond is called a hydroxyl group. The molecule's functional group, we classify the molecule as an alcohol. Our hydroxyl group, we noted, was a polar bond because it can hydrogen bond. All right, and so although we would consider alcohols a polar functional group, when we're given a specific molecule here, there's kind of a push and pull going on here. Because yes, that functional group, that hydroxyl group is polar. But what's going on in the rest of the molecule, right? Alcohols also necessarily have these hydrocarbon tails here. And what do we think about the polarity of that hydrocarbon tail? Polar or nonpolar? Nonpolar, right? Only carbons and hydrogens. Only capable of those dispersion forces. So we kind of got this push-pull going on with our alcohols. Yes, we consider to be alcohols a polar functional group. But when I'm considering an alcohol and whether or not it's, say, soluble in water, soluble in another polar solvent, we got to look at the molecule as a whole. It's going to depend on how long that hydrocarbon tail is. All right? So let's then think about, again, we're going to address our polarity issue. But now we're going to compare this 2-carbon alcohol to this 8-carbon alcohol. All right, and we're going to think about the polarity of these molecules. Which one do we think would be a more polar molecule? One of these is soluble in water, the other one isn't. Which one do we think, left or right? The tiny one, right? So our smaller hydrocarbon tail, this one is more polar. All right, aka is soluble in water. Our other one is less polar. It is indeed insoluble in water. It will form 2 layers. And what was our reasoning for why it was less soluble in water? What's the feature of that molecule? The longer hydrocarbon tail, right? Yep, exactly. So, because we have that longer hydrocarbon tail. All right, so then what about the boiling points of these molecules? Which one is going to have the lower boiling point out of the 2 of them? Okay, so up here we were talking about using boiling point to compare the strength of these intermolecular interactions. But there was a super important caveat that we had, which is it only works for molecules of similar sizes. All right? To be clear, octanol here can hydrogen bond with neighboring octanol molecules. It's just this hydrocarbon tail is so nonpolar that that's going to influence its interactions with, say, water molecules. All right, but they both can hydrogen bond with one another, and this one has an even longer hydrocarbon tail. So in terms of our boiling points, let me use a different color. Okay. Ethanol, we had said, was around 78 degrees Celsius. Our octanol is more like 195 degrees Celsius. So quite a bit higher of a boiling point for octanol. All right, so ethanol has the lower boiling point. Octanol has the higher boiling point. And why is that? Simply because it is a larger molecule. And that's always the case. Given a specific functional group, a larger molecule containing that functional group will always have a higher boiling point than a smaller molecule containing that same functional group. So if we had our ether, and instead of doing a 2-carbon ether, we had an 8-carbon ether, it would have a higher boiling point than that 2-carbon ether, right? So when we're looking at a specific functional group and then increasing the size of that molecule, we're always going to increase our boiling point. If we're looking at similarly sized molecules, then we can compare their polarity by using boiling point, right? But they got to be of similar size. Okay. Now we're going to do what we're sort of going to always start with here, and that's our nomenclature. There isn't too much that we have to introduce here for our nomenclature, but let's start off with a simple example here. First step in nomenclature is always to find that parent chain. We're not going to add anything new here, but maybe we just want to re-emphasize something that we discussed with our last functional group. We're going to find that longest set of continuous carbons that contains that functional group, right? So I know looking at this molecule, this carbon is going to be part of my parent chain because I'm going to find the longest continuous set of carbons that contain that functional group. And now we have a new functional group here, that hydroxyl group of our alcohol. And so we're going to use a different suffix than we've used for our previous functional group. For alcohols, we use this ending OL. So if I'm going to name this molecule here, what's my number of carbon prefix for 2? So F, all right? But it's not just ethol, it's ethanol. F-A-N-O-L. All right, so the F is our number of carbon prefix. The OL is that hydroxyl functional group, our hydroxyl group. Then what is the AN in our name telling us? That we have all carbon-carbon single bonds. If there was a carbon-carbon double bond in there, it would be an ethanol, all right? So we have this AN in our name, and this indicates all carbon-carbon single bonds. okay? So not just ethol, but ethanol. All right, let's do a slightly more difficult example here. Everybody take a second, find the parent chain in that molecule. All right, these 4 carbons. Step 2, we're to find and name our substituents. And here we got nothing new to add. We'll have our same substituents that we've had before. So for example, this 1 carbon group right here would be a methyl group. Right, our hydroxyl is not considered a substituent. That's our functional group that goes at the end of the name. All right, now we're going to number our parent chain. And we don't have anything new, but maybe we want to emphasize something we discussed with our last functional groups, alkenes, which is that we prioritize that functional group in our numbering. So when I'm numbering this molecule, I'm not going to look at my methyl group. I'm going to prioritize that functional group, making sure that it gets the lowest possible number. All right, I'm going to leave a little bit of room here because we are going to complicate things a little bit with a future example. But the last step, as always, is to just assemble the name. All right, so we would have 3 methyl. We're going to, just like we saw before with our alkenes, we're going to indicate the location of that functional group. So 3-methyl-2 butanol. All right, and an equivalent way, or rather a perfectly acceptable way to do this exact same molecule would be to move that functional group locant into the back half of the name. So 3-methyl-butene-2-ol. Either of those are perfectly acceptable. All right, let's do another example. But now I'm going to put not 1 hydroxyl group, but 2 hydroxyl groups in the same molecule. All right, I have these 4 carbons. I'm again going to number such a way where I prioritize that hydroxyl group, putting the lowest number in my name. All right, when we build this here though, now that we have 2 alcohol functional groups, how are we going to do that? What prefix do we use to refer to 2 of the identical groups in our names? Di, so this would be a diol, right? 2 alcohol groups in the same molecule, that's a diol, and that's what we're going to build into our name. So this would be 2, 3 bute and diol, because of those 2 hydroxyl groups. All right, but this isn't quite right. Looking at this name here, we're running these two consonants, A and D, together. And we've seen this before in our nomenclature. Do we put two consonants next to one another? No, we're always going to retain a vowel in between them. So it's not butanediol, it's butanediol. Okay, we're going to keep that vowel so that we don't run those two consonants together. Cool. All right, so the next example that we're going to do, we're going to use this nomenclature of alcohols. We really haven't introduced much new at all. Really just the new suffix that we have on the end. All of our other rules are the same as what we saw for our last functional group. All right, but we are going to use this as an opportunity to talk about molecules that contain more than one functional group. All right, so how do we name multi-functional group molecules? Alright, so let's take a molecule that contains both a carbon-carbon double bond and a hydroxyl group. Alright, in order to name these multifunctional group compounds, we need to consider the functional group priority. All right, so what do I mean by that? It turns out that in the world of organic chemistry, there is a master list of all functional groups, and they're ranked from highest priority to lowest priority. What we're going to do is create like a little bit of a subset of that list, and we're going to add to it every time we introduce a new functional group. All right, so this is our functional group priority list. You can Wikipedia this to see it for all of our functional groups. We're going to make a much smaller list right now. Again, we're going to rank from the highest priority to lowest priority. And there's three functional groups that we've discussed in depth thus far in your organic chemistry career. Those are alkynes, which are our lowest priority group. Those use that YNE or just YN ending. We also have alkenes. Those are the next one up on our list with that ENE or EN ending. And then our highest priority functional group at this point in the course are those new ones, our alcohols, with that OL ending. So how is this list here, this functional group priority list, going to influence how we name our molecules? All right, well, much like we said, we're going to prioritize that functional group when we number our parent chain. We're going to add here this caveat that for multifunctional group molecules, you are going to prioritize the highest priority group. Right? So what this list tells me here is in a molecule that contains both a hydroxyl group and a carbon-carbon double bond, The one that's more important, the one that I'm going to look at when I number my parent chain, is that alcohol group. That's my highest priority group. So going to our molecule here, I'm going to find my parent chain, these 3 carbons. I'm going to number my parent chain in such a way that prioritizes that higher priority alcohol functional group. All right, and now the last thing that we're going to need is, because we have these 2 suffixes that we're going to be stacking in our name, both the en and the ol ending, how we're going to have to do that is using that back half of the name locant method, right? Up here we could have had a choice. Either one of these are perfectly acceptable. When we have those 2 functional groups in one, where specifically our double bond and our alcohol in one, we're going to have to put the locant in the back half of the name. So this molecule here would be prop for those 3 carbons. Then 2 to indicate the location of that carbon-carbon double bond, 2-ene, 1-ol. Prop 2-ene 1-ol. All right, I have the location of my carbon-carbon double bond and my hydroxyl group in that molecule. And importantly, for my numbering, I prioritized that highest priority alcohol group, giving it the lowest number in my name. All right, and like I said, we'll add to this list as we go throughout the course here. All right, every time we introduce a new functional group, we'll indicate where it falls on our priority list. Cool. All right, so we learned how to name stuff, and then we talk about reactions. What we're going to start with our alcohols is a review of the reactions that were covered in the first semester. These are ways that we can create alcohols, starting with alkenes, what are called hydration reactions. All right, so hydration of our alkenes. What we're going to do is create a little summary list, little summary reaction wheel at the top. There are 3 sets of reagents that we could use in order to hydrate alkenes. I'm going to put a little reaction wheel up there with 3 sets of arrows and 3 product spots. This is just a nice little summary of these 3 hydration reactions that we're going to cover. All right, and then we're going to sort of go through and address each one individually. We're going to start first with what's called the acid catalyzed hydration. And this is where you react your alkene with water. You're going to hydrate that alkene. But importantly, it won't react all by itself. You need an acid catalyst in there. So you use this dilute solution of sulfuric acid. All right, so we got a bunch of water molecules and a few sulfuric acids to acidify that solution. Cool. All right, we're going to talk in depthly about this reaction here, our acid catalyzed hydration. So I'm going to leave some space to sort of fill out this wheel as we go. Again, this is just meant to be a nice summary of these 3 reactions. And now we're going to do a deep dive on that acid catalyzed hydration. So this is the simplest of our reagents. This is a fairly simple reaction to understand meaning one that we can actually do our full reaction mechanism for. All right, so let's take a simple example. We'll sort of graduate to that more complicated example in our reaction wheel. I sort of strategically use that molecule, but let's start with a simple alkene. We're going to react this with water and sulfuric acid. All right, and what alcohol product are we going to get? Let's see if we can't figure this out by looking at our reaction mechanism. Okay, so our goal is to get good at our reaction mechanisms, understand our reaction mechanisms, and part of that is going to be to think about our conditions that this reaction is occurring in. So this reaction here with that sulfuric acid means that this reaction is occurring under acidic conditions. And we're going to talk about a lot of reactions that occur under acidic conditions. So we want to think about what they have in common here. All right, so in order to be a reaction that occurs under acidic conditions, in order for the conditions to be acidic, there's sort of a simple rule, which is we can have no strong bases in that reaction mechanism. What's an example of a strong base? Can anybody give me one? So hydroxide would be a good example. If we deprotonated an amine, that nitrogen with that negative charge is an example. If you were to, the strongest freaking base that you'll ever see in your life would be a deprotonated carbon here. Our strong bases, note, a common feature is that they have that net negative charge. All right, so when we say no strong bases, we should have no negative charges. All right, there are a few exceptions that we can note. Chloride, bromide, and iodide are just such crappy bases that it's okay that they have negative charge. But nonetheless, so this is kind of this simple rule that we can use to make sure that we're drawing our reaction mechanisms correctly. All right, if we have a reaction that takes place under acidic conditions, you can't have any strong bases under acidic conditions, which means that we are going to know if we did something wrong in our mechanism if we see any negative charges in there. All right? So step one of this reaction is going to be using that acid catalyst. All right? Our sulfuric acid will react with water to create hydronium ions. So under acidic conditions, if we need something to play the role of an acid, of a proton donor, one of the things that we can use are those hydronium ions. Those will definitely be existing under acidic conditions. All right? And so that's what we need. We need a proton donor in that first step. That double bond plays the role of the nucleophile and grabs that proton. Everybody's going to take a second. Draw me the next step in our reaction here. Or rather, what our intermediates structure looks like. Okay, so I have, this is a bond breaking arrow. What would this arrow be? Breaking or formation or both? This is both. I break that carbon-carbon double bond, but I form a new carbon-hydrogen bond. All right, let me actually make these different colors. I put the hydrogen on that first carbon, because I'll put a carbocation on that second carbon. And remember that carbocation is going to want to form on that more substituted carbon. Okay. I'm going to be adding a hydroxyl group, but I can't have hydroxide in my reaction mixture. So my nucleophile is that weak water nucleophile. Luckily, that carbocation is a very strong electrophile, so it can react with that weak nucleophile water. All right. But we're not quite done yet. We're trying to create our alcohol product, but when water gets added on to that carbocation, it still has that additional proton on there, right? It's got 2 hydrogens that it brought along with it. When we did our bond formation here, whoops, we've turned one of those lone pairs into this carbon-oxygen bond, which is now giving our oxygen that formal charge of +1. All right, so in order to get to our alcohol product, we got to get rid of that hydrogen. We got to deprotonate that oxygen there. So in order to do that, we're going to need a base in this reaction mixture. But as we said, in order to be acidic conditions, we're not allowed to use any strong bases. So if we need a base under acidic conditions, we're going to have to use a weak base like water. We can't have hydroxide, something we would normally consider to be a base, because this is acidic conditions and no strong bases are allowed. So in order to do our deprotonation here, we're going to use a water molecule to do it. That'll just replenish the supply of hydronium ions in our reaction mixture. So we can see that acid is not actually consumed. It's consumed in the first step, but then generated in the last step. So it's a catalyst not actually being used up in our chemical reaction. Okay? But again, we have our carbocation intermediate, that carbocation forming on that more substituted carbon. All right, so just to kind of finish out our chemical equation here, to summarize our acid catalyzed reaction. Boom. All right, where that hydroxyl group is added to the more substituted carbon about that carbon-carbon double bond. All right, we're going to talk about a lot of reactions that occur under acidic conditions. And again, keeping in mind this no strong bases rule is going to be important. We're going to need proton donors. We can use a strong acid for that, but for our base, we need to use a weak base under acidic conditions. Cool. We'll pick up with that next time. What's up?